Well, thanks everybody for coming. Welcome to this week's Math Club for Adults. I don't usually do this, but I'll mention the date. Today is March 26th, 2020, and today, we're in the midst of the SARS uh, COVID-19 pandemic, and this seems like a good time to talk about data, and maybe we'll be able to connect some of our conversation to actual problem solving. In fact, today I think I'm going to give an abridged, sort of quote unquote lesson here. I'm just going to talk about what it is that I see happening in statistics often. What are the major lessons that I try to at least begin sharing with my young students who may, one day go into statistics, and I'll share several stories that I go through as I teach conditional probability and statistics, and maybe some of these will help some of you formulate better conceptions of it, because my opinion is statistics is one of those things that there is more creativity than you think involved in it. So each time you get to see something fresh and new from another person, it's a chance to understand it a little bit better. So this was by the way, Glia was one of my old companies that I was developing for a while, and so that's the branding up in the upper left hand corner. But this is a story that's actually happened in close to the way that I'm going to explain it here, which is that you had two baseball players who were very good during one season. But one of them had, a little bit better stats than the other one. But when you began to look at things situationally, it was the one with the lower looking overall stats who seemed to have the better situational stats. This Albert Pujols guy seemed to do better during day games than Paul MVP, and better during night games than Paul MVP. So why, under what conditions would you ever choose Paul MVP before Albert Pujols? And of course, Albert Pujols, and I figure even though he won about 3 MVPs, that he was probably shorted a couple during his career. Um, but so this is an example of something that happens that's called a Simpsons Paradox, which is that you have a trend that seems to flow one way overall, but when you dig into the data, it's actually flowing, the other direction on the more specific level. And so it can give a false sense that one thing is better than another, or it can give you it can kind of play misdirection in your mind as to how the variables work. And it takes I think it takes a lot of practice, asking questions like, could there be another overriding variable that we're not looking at? Some people might not think day games versus night games matters, but you never know until you dig into the data, and the data might chop up in all kinds of different ways. So yeah, that's one example. That's a Simpsons paradox. You definitely want Albert Pujols. If you were picking a player from, I don't know, 2000 to 2010, that was definitely the player to pick for that decade. At least before Barry Bonds did his went insane, became the greatest player ever thing. But anyhow, this is a story right here that actually relates a lot to the current, viral epidemic. And
Why would you pick the one over the other?
oh, because specifically, there is no circumstance where the guy who was given the MVP was going to be better. He was worse than Albert during day games. He was worse than Albert during night games. He was worse at home. He was worse on the road. There was a season where if you broke it down in all these ways, it was just very clear, um, that one player was better than the other. And it's happened that way a few times historically. Um, but it happens to be that the player who was second best had more of the best circumstances, right? Like if it's better to play at night, they had more night games, right? You may have a
Okay.
situation like Wrigley Field where almost all the games were day games because they didn't even put in lights till decades after everybody else did, right? So anyhow, yeah, if somebody else is getting the best of it, it's also a good example of why you should play only the best games, right? Yeah, no matter how good you are at playing games, you should only play the ones that are the best, and in order to have the best results. But this is an example And just to mention, I stretched these discussions out over longer periods of time with middle school students to start to get them used to it. But I'm going to go faster here. I assume that a lot of people here have seen at least some of this, but this is the one that I'm going to dwell on longest. Here, let's say that we have a town of 100,000 residents, and we have some sort of an infection going on, and 2,000 people are infected. And here we have a less serious disease than COVID-19. We have um, uh, the people who have the symptoms. Their left pinky toe swells up to the size of a watermelon, and so they have to walk around, and it's kind of inconvenient. Just go da-doom, 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 and they have to buy bigger shoes, and that's the inconvenience. So 2% of people in this town have whatever this is, however it's transmitted, and you have tests. And now these tests aren't perfect. If someone is infected, then the test is 99% accurate. If someone is not infected, the test is 95% accurate. And I'm going to tell you right now, part of the reason I thought of doing this was because I was trying to explain conditional statistics in a Facebook thread, and I was finding it very difficult. I was clearly talking with a person that didn't have a lot of experience with statistics, but didn't understand that they didn't have a lot of experience with statistics, right? Like the kind of person who takes like one college course but has never done anything in the real world with statistics, but becomes very overconfident thinking about it. I was trying to explain, well, we need to know the efficacy rates of these tests in order to be able to say much of anything, and I have not found a single data source yet that gave me some confident sense of these are the efficacy rates of the tests. And in fact, there was just an article that came out today where um, I don't know if you actually I'm going to look over at my feed real quick. Okay, Spain bought 640,000 testing kits from China, and they're apparently fake.
Oh,
So so
Are you kidding?
not even kidding. At least that's at least the claim from an article from Spain. That's the claim. So I guess I don't know beyond the claim, but it is in a newspaper article. Or
from the Chinese government, or
It was a Chinese manufacturer. But I don't know, like, I guess, I mean, I read somewhere like the Chinese government gave like a list of approved vendors or something to people. I don't know if this was or was not on the list.
wow.
And China is, of course, famous for fraudulent products.
yeah, unfortunately. So but then even otherwise, let's say tests in the United States, the quality can vary, right? And we have many different laboratories processing the tests, and then we have this weird consideration of, like how much does viral load matter? We don't even know, like the people who are getting, like, clearly there are people whose bodies, and all our bodies are constantly under attack by all kinds of things, and we process some of these better than others. We handle some of these better than others. Some people are apparently processing it without any symptoms, and that's wonderful. But of course, we don't know easily how to tell, how many people have had it who have been tested. So do we even know, what the true positive percentage, the true negative percentage are for these tests? And I'm going to show in a spreadsheet how much that matters. I've kicked around the numbers here. Originally, part of the reason I actually created this exercise is in class, I give this circumstance to the students. We talk through the situation. We make a grid of numbers, and we count up the people who are true positive and true negative, false positive, false negative. But before we do any of the calculations, I ask, you've gone in to see the doctor. The doctor tests you and you test positive. What is the percent chance you have Sarkisov syndrome? By the way, just for anybody who knows, I picked Sarkisov because one of my teachers was named Sarkisov. So, anyway, Yeah, I asked people to estimate, and people look at these numbers 99%, 95%, and most of my students guess, above 90%. Occasionally, I will have a student who has a parent who's a researcher who knows better, and they'll test lower. But I would say that, probably 70% of responses have been here, and very, very few have been under 50%. Like, I would bet, no more than about 5% of my students have responded by saying under 50%, but the correct answer is approximately 29%. If the doctor says you've tested positive, there's only a 29% chance. And here's the thing, you can't know this without doing the math. And here's a very good real world example. If there's several different breast cancer tests, right? There's a first order, there's a second order. The first order test is less invasive and less expensive. But if you test positive, there is still only a 10% chance that you have breast cancer. And part of the reason why is because the number of people who don't have breast cancer overwhelms the number who do. So, without a test that's really, really high accuracy, without like a second order test that gets into tissue or something like that, it's very, very hard to tell. And so here's a spreadsheet real quick. I guess I don't need to make it big. Can everybody see that and read it well?
Can
Okay.
you make it slightly larger?
Let me see. Where's the? Oops.
You could
Bottom
maybe
right,
you could zoom it.
there's a magnifying glass.
Right.
Yeah.
And I know the control percentage stuff, but I was so much better at old Excel because I just haven't learned new Excel as much. I think if I just control plus sign, nope, that's not doing it.
Yeah.
Okay. Well, where is it, Amanda? Oh,
Bottom
down
right,
here.
yeah, down there.
Got it. Okay. Thank you.
You're welcome.
There used to be a number up here that gave a percentage, but it's probably on one of these other pages. Anyhow, there we go. Okay, that's easily readable. Okay, so if I were to, so we can see that the number of positive tests of people who are infected out of those 2,000, it's a little less than 2,000, but there are more false positives from the non-infected residents. And so we get 29% in this case. We could change that number. Let's say that the positive tests were only 98%, and the negative test rate was only 92%. Correct. Now it goes down to 20. Well, what if only a 0.5% of the population? Oops, I should give that some decimal points.
Go to home.
Thanks.
And then number. Yeah.
Yeah, there we go. If we make a 0.5% infected, now only 6% of people who are told they test positive, give or take, only 5.8% actually have Sarkoff syndrome. So these numbers are really, really crucial to know. In fact, and I think this is part of the reason there are sort of conspiracy theory elements to something like this. One, we know that there is often, false information. There's often false information for government purposes. We think that that's probably the case with China and Chinese data. There's often, false information for corporate purposes. We just don't know how good our information is, and therefore people will begin to paint all kinds of pictures. But really and truly, if we want to know, we've got to try to dig down into data. But people are when people don't know how how to attest for the quality of information, they don't know what to think about it. And then you have people making poor decisions on the whole. I'm going to point something out too. From a friend sent me a spreadsheet. My friend Emily, that John and I went to high school with, we were on math team with years ago. She sent me a spreadsheet that has at least since early in March, updated information state by state on the number of people who tested positive, negative, pending, hospitalized, dead, total number tested. And I'm gonna, just one simple, there was some numbers that drew my eyeballs. I looked at Alaska. Where's Alaska? Up here, AK. And immediately my eyeballs were drawn to the fact that they may not have been updating numbers every day, and then they have one here that's inverted. Clearly, the number of negative tests did not go down from one day to the next. So, there's a little bit of dirty data in here, and we don't know exactly, what the problems were. But my thought, looking at these lines right here, was, wait, 6 out of 400. That's 1.5%. If you have a test that is 98.5% accurate, you would expect that many false positives. So until you, really and truly, this could be a non-existent virus, or a virus that is non-existent in Alaska, at least, right? It could be it could be that nobody in Alaska has this thing. Now, I doubt that that's perfectly true, but it might actually be, right. Some places remote as Alaska. Some place where people are as spread out. There's only a few 100,000 people in Alaska. They're very spread out. And you have one hospitalization and one death. And how did they attribute that death? And, was it a false positive? Who knows? Who knows? In a state that's larger like New York, we may have a better idea of what's going on. And of course, New York is also, part of the contiguous United States. But looking at what we see in New York, I suspect this is better data. But even now we look, and instead of 1.5% positive tests, we have rates that look like
That data doesn't seem right. If that's a running total, the spike going from the day before my birthday to my birthday just seems crazy. 92 negatives to 2,700 negatives overnight.
So. But here's the question now. Just as we've been talking about various things that we might call biases in the data, and there's a bias can mean a whole lot of different things. Are we testing mostly only the people who come forward with symptoms? And was it that at the very beginning, we began hearing about celebrities? Tom Hanks has it. This member of this government from this country who met with Trump has it. It may be early on. It was easier to get a test if you were some form of VIP. But now, primarily, now that mass testing is being rolled out, the number of the people who are getting tested first are the people who show symptoms within the basket of symptoms that we have labeled COVID-19.
One of the issues is that a large percentage of the people that have this are asymptomatic, and of the ones that have symptoms, a very large percentage of those, the symptoms are mild, and you don't know that it isn't just a regular flu.
Right. And so until those people are tested, we don't actually know what these percentages are going to look like. And so there's a heavy bias according to who is getting tested.
There's a town in Italy where they tested everyone regardless of symptomology, and they found about a 50% asymptomatic rate. On Diamond Princess, the confidence interval was more around 30%, but they did have a much older population there.
Yeah, I think I read 20% for Diamond Princess, but that wouldn't surprise me. Yeah, so within various populations, we have completely different kinds of testing. We have different levels of testing in terms of ubiquity of the testing, and it becomes very, very hard to get into the detail of exactly what it means. In Alaska, it was 1.5% positive. Maybe no one in Alaska has it, and the test has a 1.5% error rate. But then I have to ask the question, are they using the same test? It looked like, at least early, I haven't quite followed this controversy, but I know that because of the regulations in the CDC and the FDA, it was basically illegal for other people to make tests. And Amanda, given that you're a researcher, I remember us discussing this, and you remember the details better than I did. What happened there exactly?
So they invoked like an emergency piece of legislation that was supposed to make things better, but it made things worse because it meant that all the tests had to be approved under a certain regulation by the FDA. and the CDC was developing a test, and the CDC botched it. And so at that point in time, there was only one supplier, and the one supplier was a point of failure. So it was several weeks later that they started approving additional people to run the tests.
If there's a
And
silver lining, it means that our tests are probably more uniform, and we may be able to get good data from that. But of course, it meant a several week delay in large scale testing, and that's turned out to be pretty ugly. But again, like I said, without knowing like how slanted, let's say that you have two populations. There are all kinds of diseases that are more in one population than another. For instance, sickle cell anemia is mostly within Black population, and then oh, I can't remember the name of it now. The reason
fibrosis.
that say again,
CF.
Which is
so very high carrier cystic fibrosis, so very high carrier population among Caucasians.
And there's some genetic abnormalities that are more common within the Ashkenazi Jewish population. And so when people get married, they're very likely to get tested for that in order to make sure that they are able to have healthy children or have a higher percentage chance of having healthy children. So, there are all these kinds of, we have to understand that if we're testing different populations, we get different results. So these percentages probably don't mean anything on the whole if what's happening is all the people who are sick are the ones going and getting tested. It may be that most of the sick people have been tested, that we've counted them, and that it may be that 30,000 positive tests, maybe there are a few false positives. Maybe we'll call this number 28,000, but maybe there are only 50,000 people in the state that have it. Or maybe 100,000. Yeah, I know a lot of people are asymptomatic, so maybe we say 100,000 people have it. Whereas out of 12 million people, I can't remember how big New York is. I'm probably making this number up. I'll say 12 million people. So that's still less than 1% of the population. And if a huge number of those people have already been tested, then it's not going to look anything like 30% of the population having it. Then again, I might be wrong. Maybe they are testing almost at random, and 30% of the population does have it. But how do we know? How do we get that data before knowing how it's done? And so far as I've seen, that data is not easily available, and it's not even clear to me that there are enough people well trained in statistics to know how to create something like a questionnaire within a hospital. And they may just be too busy also, right? But to make something like a simple questionnaire that would ask these questions in order to help us figure out how to undirty the data, to clean up the data and make it meaningful. So anyway, that was a lot of my initial thought in preparing a discussion for today. I didn't know if anybody might have like ideas on one, where to get data, and two, how to better analyze it to know what's going on, what might happen.
I have a question for you.
Yeah.
I want to get an intuitive understanding of your spreadsheet. If you went back to that spreadsheet and you made the infection rate 50%,
Mm-hmm.
then the true positive would be much higher.
Yes.
So really what's happening when we look at problems like this in the future is we have to understand that the infection rate is critical, because if the infection rate is low, then the non-infected false positives have a much greater impact.
I'm glad you brought this up, because I actually meant to draw a picture that I think that usually when I draw this picture, I think everybody feels better about an intuitive understanding of it. That's absolutely true. All these variables matter. Every single one of them goes into telling the story. If you have a population, let's say the circle, it's like a Venn diagram, represents the people in a region, and then this red circle represents the people who are infected. And I'm not saying whether that's 0.1% or whether it's 50%. But for right now, that's the people. And then we have this test, which is 90-something% accurate, and it captures all of the people here, but it also captures a few percent of the people who are not infected. But this blue circle, this is the tested positive circle. The red circle is the infected population. And so, this is Bayes identity. This is where we get into, Bayesian statistics. Bayes identity says that the probability of A given B is equal to the intersection of A and B divided by the probability of B. And let's talk about that in terms of these sets, because I think a lot of people get a little frightened of this formula when they first see it. Though I can see that I've got mostly statistically trained people with me here tonight. So here, the probability of A given B. The given B is, in this case, the positive test. And so we're not really looking at the whole population anymore. We have created a conditional focus, right? We're no longer asking about anything outside that blue circle. Now we're looking inside the blue circle and saying, what's the probability that a person has it, which is much larger than the probability in the general case outside of the blue circle. So what we're actually taking the ratio of is the intersection, which is where I drew those lines in both the red and the blue, divided by the blue, which is just means that we're just examining the people who tested positive. And if that red circle, if it grows and shrinks, yeah, that affects things. The infection rate definitely affects things. Also, the percentage, accuracy affects things. How much do we cut off that little sliver out here, and how much do we include on the outside? The better your test, the smaller that gray area. The better your test, the closer you can get to 100%, with just the red shaded area dominating the blue circle.
How about tests like, I don't know, genetic sequencing? Does anything of this type apply to those?
Yeah, I would say absolutely. In fact, just our examples earlier, the one that always jumps to mind for me is sickle cell, but cystic fibrosis. If you're already narrowing down to, whether it's a racial or ethnic population, if you're already narrowing down, your percentages definitely change. All of or lots of defects are more or less concentrated in one population than another, just because of family histories and maybe also geographies and all the things that happened historically. So yeah, absolutely. Almost every condition matters is the way that I think about it. It's rare that a condition has makes no difference at all. This is part of the reason why a lot of data science is actually to imagine what are 100 things that might or might not be variables, and then to go in and begin slicing up the data into 2 to the 100th power different categories. Probably not that finely, but to chop it up into categories, sometimes to chop it up a little bit, just 3 or 4 binary categories at a time, and see what you notice there. And actually, here's a good story that relates to that. A lot of the healthcare debate has always centered around life expectancy. Which nations have the best life expectancy? Doesn't that tell us something about their healthcare systems? And the answer is maybe, but it looks like probably not, because 4 binary variables: how much people drive per country, how much they consume alcohol and other drugs, how much. Let's see if I can remember them all. Oh, obesity rate, and there was a 4th. I think I found this on
Malnutrition or something?
I don't think it was that specifically. I'm actually referring to the comparison between Japan and the United States. there were four variables, and it was Freakonomics, I think. Oh, somebody just asked smoking. I think that was actually it. Yeah, James says
I
smoke.
thought that too, but then I thought that would have been is covered by alcohol and other drugs. Maybe smoking is big enough to merit its own category.
I'll be honest. I think that when I heard this from Freakonomics, they just said alcohol. I think I threw in the other drugs part. But yeah, those four variables, if you took those variables out and you said, well, we've got 2 to the 4th different categories of these different variables, that like 15 or 16 of them, you live longer in the United States. It just happens that whereas 30% of people in the US are obese, 3% are obese in Japan. We drive 12,000 miles a year. They drive 2,000 and they walk a lot. Right. So, when you have so many people crammed into the low risk groups, yes, they tend to live longer. But the fact of the matter is, if any one of them moved here and didn't change their risk profile, they would live longer in the United States. And it's been studied, and primarily what it turns out is we have the best heart care in the world. We have defibrillators everywhere. If you have a heart attack, you're better off being in the United States than anywhere. And because that's such a high cause of death, especially as people get older, that winds up mattering a lot. So yeah, so that's an example, and until we begin chopping up the data, we just don't know. And I think that this is really the case. This is what is going on with sort of we have mass debates going on about interpretations of a lot of the data, and I think that it comes down to the fact that most probably just a tiny proportion of people understand all the chaos that happens when trying to get to the bottom of conditional statistics. And they don't know what the right questions to ask are. They don't know what might be wrong in the data. And then they just sort of default to arguments that they might have wanted to make anyway, whether it's a partisan argument, a healthcare argument, or just, something that they've read from an expert that they trust. So I can't remember where that question started. I don't know if I have walked that thread to a reasonable end or not, but it is good to make a spreadsheet like this, and that was exactly the right thing to do. Is what happens when when the infection rate is so high? Obviously your positive test percentage, it approaches I guess your true positives asymptotically, I think. Oops. No, I guess it approaches 100% asymptotically. Oops, I was wrong. Anyhow, it gets better and better.
Change the true positives so they're equal, and I think you'll get.
You mean both 98%?
I think you'll get an intuitive, yeah, both. I'm beginning to understand the spreadsheet intuitively. That infection rate is critical, and the difference between the true positive and true negative is critical.
Yeah, the difference between the true positive and the true negative, that is like proportion of the gray areas. Yeah, those are the two gray areas over here. But the red area is, the infection rate is the percent that the red area makes up of the whole circle.
I've sort of been kind of curious, in this context that we're in right now. I'm just kind of wondering, I've seen specificity of around 80% for a lot of the tests that we have right now. Of course, we're getting a very biased sampling of the population. Like in Texas, for example, you have to have a fever, you have to be over 60, you have to have a cough or one other symptom to be able to get a test at the drive-through center that's down the street from us. But I'm kind of wondering, if you're looking at a sort of pandemic scenario, is it the case that you would much prefer a test that has a high false positive rate as opposed to a false negative rate as far as containing spread?
And this may be my fault, because I thought you were about to say something else at the very end. Can you say that again? Because I feel like you threw me a curveball.
So I was just wondering, like, if you're looking at developing a test, is it the case that in a pandemic, when your goal is to minimize spread, you prefer a test with a high false positive rate as opposed to a false negative rate?
Yeah, I think that's the kind of thing that, like, oh gosh, I don't think we should try. I don't think we can try to engineer something like that, right? I think that when it comes to these tests, the error rate is something that just kind of like it falls out according to whatever detection mechanism is going on. Something just kind of happens. Now, if you could know what you need to engineer a situation in the end, maybe you could do something like that. But
So I'm just trying to think, like, so with a PCR assay, if usually say I do like 36 cycles of PCR amplification, and you can kind of tell the range in which you get reliable results out of PCR. But if I bump up the cycles to 100, even if I don't have anything there, it may still look like a positive result. But if you amp up the cycles, you may also increase your detection limit.
I think Amanda has a point. Play with your spreadsheet, and I think you'll see what she's saying. If you have, if you set a high, then you're going to catch a lot of people that aren't infected, but you'll get more of the people that are infected,
Oh,
and
sure.
you're just going to sequester everybody.
Sure, I understand that part. Yeah, if you amp up the false positives, then you amp up the number of people who feel like they need to stay home. Yeah,
Right.
that's
or
true.
you just sequester them like they do in Singapore.
Right, but that has its own dangers, right? Like, how much worse is the effect on the economy then? Like, do we wind up with a virus that sometimes just would not have been that big of a deal, but because of the number of false positives, we thought, wow, this is a bigger deal, right? And that's actually one of the questions that motivated me. I still I don't have a complete opinion as to whether or not this is overhyped yet, and I'll mention I have weak opinions about the following. I think that we have a serious situation with the medical equipment, the ventilators in particular. We have a serious situation with the medical personnel. And I think other than that, what we have is a serious situation in regards to the data. I think that I don't think he made the best. He didn't give the best explanation, but I think the guy's name is Dr. Ioannidis from Stanford. Wrote an article and then he gave an interview saying that this may go down as like a historical data blunder. I can't remember the way he put it, but that we were not managing the data well in order to understand what actions needed to be taken. And that was part of my point showing the Alaska data. It could very well be that that a nonsensical fear, if you have a test that is 1.5% false positives, and of course we do have other states, and that's fortunate that we can compare the data across them all. But it is conceivable that you could have a situation where enough false positives make people think everything has to be locked down when that may not even be the case. Yeah, I tend to think that relative safety is good here. I tend to think also that if we had been prepared with every American owning a mask at home, like happens in some Asian countries, I tend to think that would have that might have even allowed life to go on relatively normally. Apparently, in Singapore, life is going on relatively normally, and that was one of the nations that had like the best containment. Once it got there, there wasn't really an epidemic.
Yeah,
So anyway,
Matthew. So
yeah.
just to interrupt here, I was reading an article where they are saying the opposite thing was true for Russia. I mean, they are passing on patients with COVID as pneumonia patients, right? So you are getting more false negative than false positive, just to keep the alarm bell lower.
Oh, interesting. So playing with the statistics to try to manage the public reaction.
Yeah, yeah.
Right, and that's the question with China. Is China, in general, economists who have studied China for years and financial analysts, almost everybody hates to study China because it's clear how much data that they just make up, or if it's not made up, they have some sort of perverse incentive within their system where people who report to make the collection of data have a perverse incentive to report falsely. They may have a perverse incentive to report falsely even the number of people in their region. There's some people who believe, and I don't even know how to weigh in on this. There's some people who believe that that China's estimate of its own population is off by possibly hundreds of millions because of incentives for local governance to pass on the wrong numbers and to sometimes include overlaps with other precincts or however they call them, prefectures. So yeah, data from China is always just so much in doubt that we don't even know. It would be very hard to correct it. And the only time that economists even want to publish on China apparently is when they get some sort of like natural experiment data that had no chance of going through any washing. But there's some point at which data is just too dirty for us to even know what to do with. There are some methods though. This is one worth looking up for anybody who's a really data nerdhead. The German tank problem. During World War II, the Allies wanted to know how many tanks. I guess the Germans were just amazing at building tanks. First of all, their tank designs were fantastic, but we didn't know how to estimate how many they had, and I can't remember if it was one specific design. I think that they made 256 of them ever, and of course, a mathematician thinks of that as a nice round number because it's 2 to the 8th power, and maybe they did maybe they made them in groups of 16 at a time or something like that. But we didn't know how many were made total, but we found a serial number and we came up, we kind of plotted the serial numbers that we found and came up with like a most likely estimate of 255. And so it was a clever way to get it the possible total when you have dirty data. But methods like that, it's like anytime you find a method like that, for anybody who's ever solved partial differential equations and even seen what the ugly ones look like, knows that if we're able to find a pathway through, we are within cases that have either been studied real hard or we're lucky. We're just lucky. There's so many ways to make data dirty that it's hard to even know where to begin a lot of times. So we can see even in just this spreadsheet, we can make things go off the rails pretty quickly with just a few variables. We can make the percent chance that you have it if you have tested positive very, very low for a lot of ailments. And so I guess this leads actually on to there's something going on right now. I think it's just starting, which is to test for people with antibodies. And Amanda, you may be able to comment on this better than I am. Amanda's the biologist in the family. I know that they've been trying to develop these. Have they begun to implement that?
Yeah, so there are a couple companies in the United States. One was just licensed, I believe, earlier this week to be able to start producing and distributing their ELISA. At least I assume it's an ELISA. But yeah, so we're starting to get that. And then Korea said that they are going to start exporting 300,000 antibody tests. I think that is per month globally, that they'll have that excess capacity.
Okay, and my theory is that's when we're actually going to find out, like if this is the number of positive tests in New York, we're actually going to be able to sample the broad population with these antibody tests. Maybe like regardless of what people are asking for or something, maybe we'll just be able to line up 1,000 people and randomly sample 1,000 people and figure out how many are infected. Then we will know the actual false positive rate of these tests and find out whether or not that 30% is actually 5% or whether it's 10% or 2%. We won't know, I don't think, until we have those antibody tests.
Yeah,
Amanda?
just to clarify, a lot of the people, you can test positive for the antibody and test negative for the virus because the antibodies persist at least for a little while after you have cleared the virus. They're your immune system's response to the viral infection. So it won't just be for people who are currently ill.
A lot of times those hemoglobins, is that?
Immunoglobins, very
immunoglobins,
close.
thank you. Right. A lot of times those can last a lifetime, but they don't necessarily have to.
Yeah, so there are some things where you get lifetime immunity. There are some things where you're immune for weeks or months or years. It just kind of depends on your immune response and also on the evolutionary patterns of what infected you.
So do we, to your knowledge, do we know yet how long we think that they last? Do we like
So
from
we
similar
know
diseases?
that antibody response is detectable at around 4 to 5 days from what I have seen. So 4 to 5 days after symptoms, not necessarily infection, but after
I guess I was
symptoms.
asking how long it lasts because I was thinking, you know, like when do we get a herd
Oh.
immunity effect?
So I don't know that we have much data beyond, you know, a couple of weeks to a couple of months. But right now, New York is doing plasma exchanges from individuals who have recovered from an infection and giving them to individuals who are currently fighting the disease. So that's a very old technique that we've used for a very long time. In fact, sometimes they've actually used serum from different species to treat humans. You can do it once. After that, you develop antibodies to that species and you'll die. But yeah, there have been instances in history where people get antibodies from horses to a disease that they are currently infected with. I don't think they would do that anymore.
Yeah. So yeah, it may be that that we're able to control the pandemic in different ways that people are talking about once we have a sense of how many people have antibodies, using like plasma injections or transfusions or however we can find a way to do it. So I just want to point this out because I was made aware of this shortly before we all got together. So this is the way things look right now. I don't have exact numbers on this, but yeah, not everybody who has COVID is hospitalized, right? Some people have mild symptoms. Some people have, you know, some people just, you know, their breathing becomes difficult because they're, uh, I mean, what's the right word? The sacs in the lungs that collapse. What are those called again?
Aviola?
Okay, the alveolar collapse, and then they get acute respiratory distress syndrome, I guess is what they call it, ARDS, and you know that's when a lot of people are hospitalized. But I was having a discussion about the rates, like you know, what is the percentage of people that are hospitalized, and you know, of course, hospitalization may lag, you know, testing, and then we have death rates that probably lag hospitalization. Apparently, about a third of people are put on ventilators, but this is the real sad news is that a third of the people go to the hospital are put on ventilators, but 70% of those put on ventilators, at least in Seattle, have still been passing away. So, you know, that's, you know, the deaths are concentrated among people who have such severe COVID that they need the ventilator, but the ventilator, it only works for a few of them. And then even then, apparently, those people who come off of a ventilator, a lot of them have permanent lung damage. They may have. I actually talked to a business partner earlier today who said his daughter had pneumonia when she was 6, and she has like 20% reduced lung function, and she'll have it for the rest of her life. She's a state champion athlete, but in a competition that doesn't require, you know, as much cardio. Which is, you know, still kind of incredible. But I guess the point is, you know, people still, you know, if you have something serious like pneumonia, there's a very good chance that you're going to lose a lot of lung function. So yeah, I had thought originally that we needed to shore up this bottleneck of ventilators and people capable of using them, and I thought that that was going to be by far the most critical factor. But it may be that that just doesn't matter much, unfortunately. It may be that the point at which you know, you need a ventilator to help you, that most of those people are going to pass away.
I
And
have a question for Amanda related to this. I've read literature and it says that the people that get very sick and have reduced lung function and have trouble breathing have experienced a cytokine cascade. Do you know what that means?
Yeah, so it's actually the case that sometimes when you become ill, the majority of damage that is done to you is not done to you by the infection. The majority of damage that is done to you is done to you by your own immune system. And so it's kind of like you have, there are a lot of situations in which you want a strong immune response, but you can imagine if there are all of these cells in your body that are now infected, and one of your body's ways of dealing with the infection is to go out and purge and kill those cells, then at some point you kill the host. If there are so many cells, and that's your immune responsive pathway. So yeah, there's a very careful balance between controlling a virus and killing the person that our immune system walks. And sometimes it gets out of control and you just are invoking huge amounts of damage on your pulmonary system or, your circulatory system as your body tries to fight the infection.
And I guess this plays into some of the comorbidities. Apparently, most of the people who die have very serious, almost everyone, maybe more than 99% of the people who die have something else going on, whether it's hypertension, lung damage from smoking, what are the anybody else? Maybe it's serious heart disease.
Diabetes.
Diabetes. Thank you. That was one of the big ones. And all of these are conditions where already you have much higher levels of inflammation going on somewhere in the body, and we've been learning more and more that inflammation has a lot to do with the body attacking itself. And if you have multiple things causing any part of the body to attack itself at the same time, then you're really asking for serious trouble and damage. So
the one exception that seems to be there, so my son was admitted to the hospital for RSV, which is also a deeper lung infection. He was put on an asthmatic pathway because usually you get RSV if you're elderly or an infant. Like, so anyone who has a brand new baby, your doctor might warn you against being careful about getting like even a common cold, because for us RSV is a common cold, but for an infant can wipe out their lungs like COVID could. One of the things I've been paying really close attention to the asthma stuff, and there's at least some early Chinese data. Again, who knows if it's very accurate, but they did look at different comorbidities, and there it looked like asthma was not one of them. Which if there was a simple inflammation issue, you would think asthma, and quite honestly, with a lot of respiratory viruses, asthma can cause a problem. It doesn't seem that that's the case here. Obviously, they're warning anyone who's asthmatic, be careful, extra careful, because usually respiratory diseases are really bad for them. But I haven't been able to find any evidence that asthma is a comorbidity that's causing an issue.
Interesting. I have to admit that my entire nervousness over this is that I'm borderline exercise-induced asthma, which is probably mostly a matter of just allergies. When I go out running, when I start running every time, especially for the first 2 or 3 months, my lungs start to fill up with fluid. And Amanda has an inhaler. I guess hers is probably about as bad as mine, but I chose not to do any treatments or steroids or anything. But yeah, I was worried about that, but I too have not noticed as much asthma data. So hopefully that's not as much of a.
Yeah, I saw that as well. I have read some stuff that's saying that one of the reasons that hypertension is such a significant comorbidity is because of the ACE receptors. Because some of the meds that we put people with hypertension on increase their prevalence on the cell surface, and that's the receptor that the coronavirus uses to get inside the cell. But I don't know if there is any experimental evidence or anything like that to indicate it's all just, as far as I can tell, people theorizing.
Right.
Hey, Matthew, one other thing is last year, Narit was working on a machine learning model that looks into this images of eye and find out if there is a macular edema in the eye based on the neural network learning model, right? I was trying to encourage him to use the same model to look into the blood and find out if he can get a pattern for the COVID.
I'm sorry. I couldn't hear you all that well with the background noise. Is
Sorry.
this? Are you talking about your son?
Yeah, exactly. He was working on a model last year which uses that deep neural network to find out the macular edema in the eye scans, right? The diabetic retinopathy and macular edema in the eye scans. So it was basically an image recognition problem, and
Yeah.
I was trying to make him work on a database where the lung is infected with COVID, and if he can find out a pattern in there.
In other words, something that can be done without administering something like an antibody test. Yeah,
Yeah,
I bet that there are people thinking about this. I know that people are talking about lung scans and lung
right.
X-rays, right?
Yeah.
Like that seems like one of the non-invasive ways to test for things. But then again, I suspect, and you know what? This actually brings up a piece of the conversation that I wanted to have, and I'm surprised I didn't remember till now. I bet that something like that works better for COVID patients than it does for the general population infected with the coronavirus, right? This is, and actually, I was wondering anybody else who might have come across any data that explains this. One of my issues in interpreting all the data that's been surrounding this is, for the flu, you have the flu, and then you have a death rate for the flu, right? But here we have different categories. We have people who are infected with the SARS-2 coronavirus. Then we have people who have COVID-19, which is a name that was given to the disease that is the symptomatic result that some people do and some people don't have from the coronavirus. I think I'm interpreting that correctly. So now, since we have these multiple categories, and then we have a death rate, right? And we see these death rate percentages. Is it 1.2% of the people with COVID-19, or is it 1.2% of the people who have the SARS-2 COVID virus? And will this number decrease as we come up with a few simple countermeasures or get our testing caught up with our population, right? So this brings us to a very major statistical point. We could have something as small as a fraction of a percent, a small fraction of a percent death rate, and we may be measuring it as something much higher. I don't know that we're doing that, but because I don't know how it is that people are deciding is one piece of data about the coronavirus infections, or is it about specifically COVID-19? And as far as I can tell from most articles I see, nobody's delineating. And I don't even know how we can solve that problem. Maybe now that we're doing other tests, but I guess you, Kundin, that you brought up that idea because there are probably a lot of things that we can do for testing that relate. It's probably easier to detect COVID-19 than it is to detect coronavirus without just getting into somebody's blood, right?
Yeah, right, exactly.
I did see. I'd have to go look at it. A study that was looking at asymptomatic patients, and what was weird about it is that it had a class of patients who were asymptomatic but had something showing up on like a lung X-ray, like the kind of X-ray you'd get to rule out pneumonia. So something was showing up. They were otherwise asymptomatic, but they tested positive. I didn't know what to make of it because, like, I would assume if you can see it on an X-ray, you
Right.
should have some symptoms.
Right.
But
This is exactly the problem. Is who is defining what asymptomatic means? Does
right.
that mean self-diagnosed asymptomatic, or expressed, as in I can't feel it, but maybe it's still there? So you're saying that
Uh,
from what you've seen, it's possible that people who are asymptomatic still have stuff that'll show up on a scan, and
Right, and that's where I'd assume like those are less likely to be false positives, whereas if I wonder if the asymptomatic cases are just false positives, right? That
Yeah.
could a lot of people are being tested because they are a relative of a person who has has
right.
COVID,
I've wondered the
right?
same thing as well. And until we know the efficacy rates of the tests, it's actually
Right.
almost impossible for us to know. But I say that, but Tanya brought up oh God, it was the Diamond Princess. Is that the name of the cruise ship? I always forget. Yeah, they had either 20 or 30% infected, and so that was probably the best case to actually say whether or not people were asymptomatic or not. And I remember some discussion that these numbers were different between the crew and the passenger quarters. because one of these had much tighter, I think the crew like all slept in like tighter quarters relative to each other. So it may be that we got some better sense from the cruise ship data. So yeah, again, I don't, I have not seen enough to tell me that that there's enough of the puzzle to really put together good numbers.
Yeah, it is sort of an interesting thing. Like it's not always clear what something means. Like there's this story they've, I don't know, probably told every grad student ever about, I think it's like an MIT lecturer or something in mathematics, an emeritus professor who's like 80 years old, and he walks into his classroom and he gives this brilliant lecture on mathematics, and then the next day he passes away and he donates his body to science, and when they look, his brain is just riddled with amyloid plaques. But that we usually think of that as, or at least historically we've thought of that as something which is a marker of Alzheimer's and neurodegeneration. But in this case, it wasn't symptomatic. Though now we think that amyloid plaques actually may be protective, not pathogenic. But I don't know. You see that with like knees too. There are people who come in and their knee x-ray looks ridiculously terrible, but they have no knee pain.
One of the things that I notice, and Amanda can comment, is this really does seem like a normal flu, with one exception. A small number of people who get it die in greater numbers than the normal flu. But otherwise, large numbers of the population have the disease and don't really notice it.
So I guess there are at least a couple of things that differentiate it from the flu. One is that we don't have as much herd immunity. The second is that regardless of the death rate, there is a reasonable percentage of people, especially young people. The people who are hospitalized but don't die are usually young people, right? But a lot of young people still need hospitalization. Maybe I think I heard numbers like 10%, but I don't want to. Again, like I personally think that we don't know the numbers yet. We have not solved the data problems that we've talked about tonight. But maybe that's a large number of people that need to get hospitalized. I don't think that the flu is anything close to like that. I've had it a few times in my life. Most people I know have had the flu, and I don't know very many who have been hospitalized over it who weren't old or otherwise compromised.
Well, the sad fact is that it is a large enough percentage compared to hospital beds that they're not being hospitalized. In Spain, they're basically leaving them in old folks' homes to die, literally, but in large numbers. In China, they send them home and they die. We don't have enough beds. In New York, they're triaging. They don't have enough beds. So if you get to the point with this flu where you need hospitalization, it isn't a sure thing that you'll get it.
Yeah. That is currently the case. Yeah, and it's part of the reason why I brought up, the percentage of people who are dying regardless of whether, even if they get on the ventilator. So the symptoms are serious enough that there's a point at which most people just aren't going to last. So the flu, the death rate amongst the flu is very, very concentrated in the healthy, but I think we're going to have, people who get kicked pretty hard, who are younger, but who don't die. So yeah, that's frightening for a lot of people. I'm going to go ahead and steer things toward a wrap up, unless anybody has a question or a thought that may relate to the big picture or the general statistical lessons here. Okay, and I'm going to say one more thing about conditional statistics. I think that that this is maybe the largest or second largest, most effective piece of mathematics to understand in building a better world. and I mean that quite literally. The entire actuarial population, I think, is predicated on problems that are either easier to solve or are conditional statistics. I think that a lot of artificial intelligence is like that too. It's either not that interesting and just an automated process, or it winds up being a way to curve fit or do better, that largely revolves around getting around conditional statistics problems. So I think this is absolutely one of the most important lessons we'll ever discuss. And we spent maybe half our time on the minutia of the actual world event going on, but really and truly, if like my hope is that some people will watch this video and go, oh, I should get a statistics book and read through this part right here specifically, and it may be worth more than the rest of the book combined. All right, everybody. Thanks for joining us, and hope this was this was a good lesson.
Thank you very much.
Thank
It was
you.
fun.
Everybody, stay healthy and safe.
You.
Yes.
You too.